All right. Well, let's get started. I'm super excited to welcome Bill Howe here today. He is an associate professor at the Information School at the University of Washington, also adjunct in CSE and electrical engineering. His research interests are in data science, databases, data management, machine learning, and then also applied to many important domains. Also the founding associate director of the UW Science Institute. Also founded the Data Science for Social Good program there. That just pretty much anything with any relevance. Great. Here come the rest of the crowd. So he's, you know what, Bill, I'll just let you take it away.
You mentioned all these founding places. So yeah, we were involved in the Science Institute back in the day. We were trying to look at, data science across all fields, and originally I'm a database person. I published Sigma and VLDB and so forth, but eventually kind of moved into more in the social sciences, or sociology in the urban space and so forth. And that kind of brought me over to the information school. So we've been sort of eclectic, and that's one of the things I want to talk about. I had some fun trying to put this together because it kind of occurred to me that I've got students kind of working on things that are not obviously related. And so I had to think a little bit about what is the connection between them. So this is sort of a new framing that we're working with. And so it's a caveat that there's some work that's submitted and there's some work that's not quite ready for submission and so on. But I decided to take that slice rather than go back and do stuff from previous years. So that's either a good thing or a bad thing to your attitude. So overall, what I want to kind of say is, which I don't think is too controversial, perhaps even with this crowd, is that data curation is really becoming the operative cognitive task with AI, and this is arguably, in some contexts, I try to say that AI methods are becoming commoditized. I actually don't think that's quite as true as people say it is, but there are some standard patterns that we've seen. There's multi-layer networks, training gradient descent, and there's some sort of transformer architecture, and their tooling is getting really popular. So that's kind of shifting the work to where do we get the training data from? How do we evaluate these things? How do we think about the downstream consequences of these and so on? And so while we work in what is arguably applied AI, some of the patterns that we want to extract is methods to enable these kind of curation activities. And that might be, AI methods to enable curation activities to support AI downstream applications. And then also maybe methods to benefit from the kind of curation activities that we see people already doing. And so some of the areas we've been working in, I'll spend most of the time probably on this urban data, mention these some bias and vision language models that we've done recently, court records, and then I'll try to end up, if there's time, with the scientific literature, which of course is maybe the most relevant to the semantic scholar group here. All right. So I felt obligated to mention what's going on with AlphaFold that I'm sure people are pretty familiar with, but it is pretty remarkable, right? So this beast here is this 1,000 protein apparatus that controls how stuff gets in and out of the nucleus. And there was, 30% of this thing had been sequenced experimentally over the last X number of years, and that doubled since 2021 due to AlphaFold. People are familiar with what's going on with AlphaFold. Okay. And maybe more impressive, there was 100,000 structures experimentally determined over the last 50 years, and now there's 900,000 in the AlphaFold database since 2021. So there's claims about this being a solved problem and so on. But you can ask sort of what's going on here. There are a lot of domain-specific tricks in the model. So this is an example where it's not quite as commoditized as we like. They didn't take some off-the-shelf thing. They had to spend a lot of domain expertise. But the other key ingredient here, of course, is that you've got 50 years of super highly curated expert data in the protein data bank. And one point I wanted to make here too, that people are familiar with this, is that the actual input to this model is not just a representation of the sequence. The protein fooling problem, for people that don't know, is you take a string of amino acids and you try to find some lowest energy state of how it twists around in itself. And the body, the organisms are able to do this sometimes in nanoseconds, and it's kind of a mystery as to how, because if you try to do kind of a search, they have some sort of a search strategy that's able to find the right answer quicker than we really knew how to do. And so that's been a long standing, grand challenge. But, theoretically, you should be able to say, here's the sequence, and I'll just find the structure. But in practice, even with this solution, that DeepMind has offered, the input still involves these multiple sequence alignments. And so this is the same protein in the human, some sort of oxygen carrying protein or whatever. It has the same function in the human and in the fish and in the rabbit and the chicken. And the actual amino acid sequence is not identical across those, right? You can tolerate some changes in the amino acid sequence, and you still end up getting the same structure. And so that's yet another source of supervision for this thing. So I guess I just find it. Just want to point out how much of the long-standing experimental work, enables this kind of an AI model, which is you don't always see quite emphasized in some of the popular press around this. All right. So this is kind of a rare case as opposed to the common case, right? This is where it's obviously a high-value application. We spent millions or billions of dollars on this problem, and then finally we can worry about trying to design a model. Maybe somewhere a step down, but we still have kind of highly curated data, is in weather prediction. I saw this great talk recently. I wasn't involved in this work, but I saw this great talk recently by Dale Duran, where they take a fairly standard, UNet architecture here, and they do this trick by cubing the sphere, doing this little Tetris shape here and wrapping it around the sphere, and then cutting it up and using these squares as data items, and training it on the best of breed physics-based models out there, and it does okay. Is the result here? So in blue here, it's worse than the very high resolution full physics models that are the state of the art, but it's better than the lower res ones. And then like a year later, it got a little closer by doing some ensembling on both. And ensembling is really the state of the art. Everybody does ensembling. So that's great. It's getting better, and it'll probably get even better over time. But even more remarkably, it takes 16 days to train the full physics models to get a 1 month of ensemble. It takes 2 or 3 days to train this. And once it's trained, you can generate a whole month in like 3 minutes. And so this really enables different kinds of questions you can ask. You can try out different scenarios. You can compare things differently, things that weren't really feasible in the past. But yet again, the source of curation here, the source of supervision here came from, 70 years of computational fluid dynamics models, or 500 years of mathematical modeling of this thing, right? So you can't really, it's not clear how to compress that. All right. So in areas that I'm maybe thinking about a little bit more is, say, cities. But here, the situation changes a little bit, right? We don't have this kind of really perfect curation of what ground truth is. And there's maybe 2 different ways of looking at this where you could maybe get some data. One is as looking at a city as a complex system. And this is folks like Jeffrey West and Luis Betancourt that try to look at things like how does innovation scale with population size in a city? So they'll look at like the number of patents and say, like, is there some sort of sweet spot for the size of a city? And it's pretty interesting. He's a physicist, and he tries to look at like the physics of cities and so forth. It's super fascinating stuff. The punchline here is that, there are things that should and do grow sublinearly with population size, like miles of roadway. Hopefully if you double your population size, you don't need double the miles of roadway. That would be sort of poor planning. But there's other things that are more a function of the interactions between people, like business transactions or social stuff or crime, actually, where they grow super linearly with population. And so understanding some of that and sorting it out and finding these kind of exponents and showing how cities are the same and or different from other kinds of complex systems, it's really cool. It's great work. But more practically, or more what you see more commonly, is you don't sort of see it all interconnected. You see kind of an assembly of independent subsystems where somebody's looking at ride hailing, and somebody else is looking at taxis, and somebody else is looking at waste management, or anything else. And so you get all these kind of distillatory data sets, and tying them all together is a challenge. Okay. And so here there is no master source of curation resulting from millions of dollars of investment. It's all kind of ad hoc. All right, so sometimes we have this expert curated supervision, but elsewhere it's incomplete or aggregated or disintegrated. And so one idea, if you buy this curation story, is to try to help out with this problem. Can we apply some AI, AI in the small, if you will, upstream to try to help out with the curation. All right. And so let me show you a few examples of that we've been playing with, mainly led by my student Ben Hahn. So Ben had this idea of like, let's look at computer vision techniques and apply them to these urban data sets. And so one new idea is to use image in painting. And so image in painting does this kind of a parlor trick, right? Where you can scratch out part of the image and it'll automatically fill it back in. And it works pretty well. This is qualitatively, it works pretty well, which is another difference between some of these domains that we work on and what you see maybe most commonly in machine learning conferences is, they're very web-based, right? There's a lot of tasks that are based on web images. And so quantitative rigor is not important here, right? As long as it looks like a bug, it looks like it's, you get kind of a thumbs up. And in fact, the loss function and the evaluation that they use is kind of designed to mimic like human perception, and that's part of the reason why it works so well. So some little differences. This is again another UNet kind of architecture. In our world, our images, one way of casting this data looks like this, where you drop a point or build a little 2D or 3D histogram of, say, taxi rides, and you get images that look like this, and you can make 3D blocks. And so your data items are these 3D blocks, and then you can just run with this thing. And so we kind of expected to have to sort of tweak the architecture and so forth, but it actually did work pretty well out of the box. So we were a little surprised by that. One trick we did do though is that because of the sparsity, in general, there's no one in this world, no one pixel is any more important than any other pixel necessarily. Here we kind of know that there's a bunch of zero bins everywhere else. We don't really want to waste time or distract the model too much by learning to predict zeros everywhere. And so we do a little trick where you sort of bias the masking to pick the dense areas and so forth. But this is a relatively minor adjustment to the way we train this, and it makes a big difference and it helps. But overall, this works, right? And so you can, if on the left-hand column here is ground truth at different times of day, and then here's some random masking that we use during training and or evaluation, depending on how you do the evaluation. And you can wipe out basically all of Manhattan, and then the model will recover it. And so in some sense, if you look at it one way, this looks really impressive. Another way, the patterns are relatively stable, right? It doesn't, like taxis at 2 p.m. It stays about the same most days of the year or whatever. So there's not that hard to learn. And so where it gets a little harder, or where the challenges are, is not so much about giving a qualitative result of does it look like this. It's in, where are the errors and how are they distributed, and can we actually use this for downstream tasks? And so that sometimes we're still sort of exploring here. This again was 3D, not 2D, so we can play games with how many time steps we include in each block. And so how to cut up this big 3D space is one of the questions you can ask. And we find this nice little U shape where, including 5 time steps. We don't totally understand why that's the case, but one hypothesis is that that's kind of enough to cover rush hour or something, right? 5 hours is some sort of unit of time where any more than that gets misleading. There's some sort of like Nyquist frequency going on here, perhaps, or something. Okay. And then the bias masking helps a little bit over the average masking. So, but the end result here is that we can fill in gaps. If you in the wild, if you find that you're missing a month or missing an hour, or there's some region or your telemetry failed, or one taxi cab company didn't report, perhaps we can sort of run this model and fill that back in. That's fine. That's cool. That's not really why we did it, though. The real reason why we did it is to be able to synthesize new scenarios that you don't see in the data record, right? So this is things like show me the traffic if there was an earthquake, right? We can't twiddle our thumbs and wait around for an earthquake to happen and get that real data. There's no way to sort of teach the model about that situation without using our domain knowledge to try to synthesize that space. And so a domain expert, somebody in traffic modeling or transportation or urban planning, can say, well, I think it's going to look a little bit like, Hurricane Sandy in the north half, but I also want to make sure that it looks like a 5 p.m. rush hour in the lower Manhattan, and then I want to sort of wipe out this area because let's say there was damage, and then kind of build this, and then ask the model to kind of fill in the gaps and make it realistic. So we haven't evaluated this, but this is the kind of where we want to go. We want to get people into the business of using their domain knowledge to try to teach models about situations that we may or may not actually encounter in practice. Okay. And so this sort of works. We had to look for kind of a natural experiment in the data set because we can't, otherwise you can't evaluate this thing. We can synthesize something and say, look, it looks good, but that wouldn't really do anything. So one thing Ben found was, there's a parade. And so if you have data from the parade on that day and you want taxi cab demand prediction for that day as if the parade hadn't happened, if you want to do that counterfactual, scratch it out. Right, and then ask the model to fill it back in, and now you've got something that looks. All this is really showing is that this looks more like the day before and less like the day of the parade. And so there's not, it's kind of hard to say that this is the right answer in some sense, but it, it fills it in and makes it look more like a regular day. And so we like this idea of mixing and matching and sort of scratching things out and sort of combining data sets in order to create more data representing different kinds of scenarios. All right. So another issue is that you may not have this individual level, like the taxi cab data. The story here is that they released it almost accidentally 10 years ago, and then they just kind of kept doing it. Almost as soon as they released it, there were like privacy violations where people could they de-anonymize, just like everything else, they de-anonymized it and were able to identify taxi drivers and riders and so forth. So it was a big mess, but then they just kind of went with it for a while. Now they've actually, since 2018 or something like that, they've aggregated it by the city block in order to try to enhance privacy. That doesn't actually do anything for privacy, honestly, but it makes it seem like it does. So they're doing that. And so in this case, maybe all we have is aggregated data. I don't really care about the taxi cab data set that much. It's just because it's such a good longitudinal data set, you kind of have to evaluate on it. But in many cases, the census data, all you have is aggregate, right? You're not allowed for privacy reasons to get individual data. So can we train a little model to disaggregate things? And this is still pretty preliminary. We haven't written this up yet, but the answer is yes, right? There's different political boundaries in play here. These are these public use microdata. There's also census tracts and zip codes and taxi zones. There's different ways of cutting up the space. And the idea is, can we take a low resolution aggregation and learn the spatiotemporal distribution at the higher resolution? And our original idea was to use these super resolution techniques for computer vision. They automatically sharpen images, right? Have you seen some of these things? So use those. And then we said, oh, we're going to use some graph learning because there's adjacency and the irregular boundaries that'll help us get things. And then maybe we'll also use some geographic techniques for learning. And it turns out that for this problem, none of this really mattered that much. Like a kind of a simple linear model worked pretty well. So we're still trying to figure out why that is. But the next step here is, rather than just going from low resolution to slightly higher resolution, if you go to a high enough resolution with high probability, there's only going to be 0 or 1, say, taxi ride per cell, right? And so at that point, you basically have the individual data. And so that's kind of a harder problem because there we're not trying to sort of predict it by region. And so we hypothesize that some of these more advanced techniques will be necessary when we take this step, but we haven't really completed those experiments yet. But you can see where we're trying to go. We're trying to say, take whatever crap people give us and see if we can kind of fill in the gaps and make it more usable for downstream applications. All right. Maybe the last thing here on urban, you don't just have one data set at a time. That was kind of my whole point with the complex systems. So everything depends on everything, right? So we did some work with the bike share demand here, and whether somebody rides a bike depends on the topology. They tend to prefer to ride downhill rather than ride uphill. Depends on the weather. You don't ride a bike when it's raining. There's the economics of it. There's time of day. There's all sorts of things going on here. And so how do we deal with that? And each one of these may have sort of problems and missing things and so forth too. So Andy's idea was take 3D, 2D, and 1D data. 3D means it varies in space and time. 2D is only varies in space, and like the road networks don't change very often. And 1D is basically constant across the city but varies in time. Blend all this stuff together, learn some shared representation, and then combine that with, for whatever actual problem you're trying to do. If you're trying to predict bike share demand, don't just try to learn from the history of bike share demand. Use bike share demand plus all these other dynamics that are encoded in this shared representation, and hopefully you get a better prediction. And that tends to work. So I'll show a result in a second here, but if you remember a few summers ago, right, there was this, I don't know how you noticed this, but there were multicolored bikes littering the streets of Seattle, and there was like this war that broke out, and they were like throwing each other's bikes in the canals and so forth. It's crazy. So and what happened was the city of Seattle said, okay, we're going to let these 3 companies come in and work, or try this out as an experiment. But their goal in doing so was to enable equitable access to transportation, right? They don't really care about helping these companies or anything else. They care about making sure we're having some benefit to the city. So how do they know that? Well, they have to sort of monitor the data. They have to kind of see, are you actually distributing bikes to neighborhoods that we think need it? So I learned the term mammal, right? So they were worried about, what if the only people using this are mammals? So a mammal is a middle-aged man in Lycra. right? So the idea is like, if we're only helping these sort of wealthy people that are riding bikes anyway, we don't really care. We don't want to subsidize these programs. So we want to make sure it's being distributed around. But there's no real way to know that unless you monitor the data. The companies are not eager and basically not willing to share the data directly with the city of Seattle, because all it takes is one Freedom of Information Act request and you can release the whole thing, right? So the customers don't like that, the companies don't like that. So they partnered with us, and we were able to kind of build a layer cake of legal protections at the university and claiming sort of research privilege to protect against FOIA requests. And then we could hoover up all the data and then release reports to the city of Seattle about equity, and here's where they're doing, here's what's happening. And so that was a lot of fun. So we had access to this data set.
So that's data laundering, right?
Yeah. I mean, we had a lot. There were some ethical issues that, I don't know if I call it laundry, but there were definitely some questions here about like whose side are we on and how are we trying to help this? Because if we start playing hardball with the companies, then they could sort of turn the plug off or make things. They did try to make things difficult for us. Like they were not interested in sharing their data with us at all. So they would sort of claim technical friction where there wasn't really any, and we'd call them up, and then they'd say they couldn't find somebody. So one of the companies was from China, and there was a claim that was like, well, we can't. I don't even know how I should say this. We can't work with you because we don't have somebody that speaks English. And so we
While saying it in English.
Well, the engineering team is sorry, they're in China, they can't speak. So we got our students from China to get on the call. be like problem solved. And so anyway, we had to do this dance to get them to play along. So and then eventually this got resolved because the city of Seattle started charging $200,000 a year to allow people to come, and so two of the companies dropped out, and now was just Lime, and then Uber bought Lime, I think, and so now it's just Uber like everything else. Anyway, so
So sorry, was it just memos or?
No, it's actually okay. So we wrote a little paper with this guy Stephen Mooney, who does this, who's more in public health and transportation and so forth, and he kind of led the paper, but we helped him out with the data analysis, and it wasn't that bad, honestly. The big thing about, I mean, now this seems obvious, like every city is doing this, but at the time, Seattle was the first U.S. place to do untethered bikes, right? It was, everything else was stations where you have to check it into a station, and that arguably sucks, right? It's ridiculous to go find a station to park it at and so forth. It's just a complete, it's a very, very different interaction. And so there had been equity analysis on the stations before, but the questions were more like, where should we put stations to make sure that there's access, which doesn't really say anything about whether they're going to be used in those places. And there's a lot of infrastructure development kind of questions. Here, there's a different problem, right? It's like bikes tend to drift downhill, right? They, you know what I mean? They accrete in the wrong places. And so the companies will come by in a van and like throw them in the back of the van and drive them back uphill and scatter them around. And so there's a choice there. They can decide where they're going to put them. And so that was the kind of lever to pull about like, are you going to go put some of the poor neighborhoods, even though the demand might be lower, but we still want to make sure there's availability, even if it might cost you your bottom line, we had to sort of keep them on the ball. And so overall, it wasn't that bad though. We did some measures about like, what is the probability that any individual person has a bike within 300 yards or something? And we did a sort of analysis and it worked out okay. Just one point. Okay, so equity and bias. There's a ton of work in fairness and machine learning over the last 5 or 7 years. We've done some of that work ourselves. One of my favorite examples is this one, which is Mark Hellenbach is at TRAC at UW. He's a transportation guy. He's the guy who goes on TV and talks about traffic in Seattle and knows everything about it. And like all of his students work at like SDOT and so forth, so he's extremely well connected. And so what this map is showing is the difference in ridership measures between two different ways of collecting data. One is the Orca card, right? The little, cards you swipe that every city has one. Ours is called One Regional Card for All, I think. But that gives you a very rich data set, right? It tells you kind of where you got on and who you are and so forth. You got some IDs and tracking. It's a very nice, it's an attractive data set to data scientists. The other way of measuring ridership is that on 30% of the buses, there's a pressure plate. And when you step on the pressure plate, you get a click. You don't know who it is. You don't know anything about it, but you know that somebody got on the bus. And so, these folks are smart enough to not screw this up. But if you took that very tantalizing data set, the Orca card data set, and started building predictive models and trying to design transportation systems on it, what have you done, right? Who has Orca cards? Yeah, probably most people in the room have an Orca card. I've got an Orca card at UW. Who else has Orca cards? Well, who else in theory?
Employees, companies.
Microsoft employees have worker cards. Amazon employees are. Who doesn't have worker cards? Right? It's people in lower income neighborhoods, right? And so if you take this data set and you, especially, you know, this one thing that I used to talk about in talks, I'm going to run out of time if I keep one of these anecdotes, but let me see if I push through, is that there's the whole notion of data science as a thing back in the day. Now we don't really talk about data science quite as much anymore, but there is this, you know, it's divorced from the actual domain, right? It's like, well, you talk to the data science team. And one of the things I got worried about was, you know, this data set falls off the back of a truck and comes over here and it looks great, right? But they don't necessarily know about the biases involved in that. In this case, you might be able to figure it out because you're sort of accessible. But if you're just at some company, you don't know if is it all customers, or is it recent customers, or is it certain customers, or whatever. So they were smart enough to check this by comparing these two measures of ridership, checking the difference, and then adjusting for those biases, which you can do. But in general, that may not be that may not be happening. Okay, so anyway, so bias is all over the place in data, and Annie kind of added that in using this kind of adversarial model for fairness. And this isn't something we came up with. This is one of the tricks that people have out there, but we adapted it to kind of the spatiotemporal setting, and she came up with some very nice metrics for fairness in spatiotemporal. But the way it works, if you're not familiar, is, you know, without these two boxes here is our regular model. And then you hang off this little adversarial model that just tries to guess the sensitive attribute. It tries to guess the distribution of, say, Black residents and white residents, or gender, although gender doesn't matter so much in this particular case. And to the extent that that model is able to guess race, you penalize the main model, right? So you're trying to teach the model to learn some representation from which it cannot be determined what the racial distribution is. And to the extent that you can do that, one can argue that you have more of a fair representation downstream. Does that make sense? Okay. So adversarial fairness, again, is a nice idea. That's one of the tricks that's out there in the world that we sort of adapted, and it works. You know, so you know, one thing you can ask is, does throwing in all this kitchen sink stuff actually help? And it does. And one step further is to say, well, what if somebody hand selected the perfect relevant variables? You know, they know topology and they know weather, but they ignore all the things that might distract the model. Throwing everything in with the kitchen sink and learning this representation worked about as well as the perfect Oracle selection of data sets. And then the cool thing the tantalizing thing to us was that adding fairness didn't screw up accuracy. And so, you know, we had to think about this a little bit, but there's kind of a free lunch here. And I think my interpretation is that the model is inclined to cheat, right? And say, let's just not put any bikes in the poor neighborhoods, and that will give me a pretty high accuracy. But by saying you're not allowed to do that, it was kind of a regularizer, right? Where the model was forced to find some more interesting solution that also maximized accuracy without just doing the simplistic thing. And so that was kind of cool. So there may be cases where fairness, we actually found cases where fairness, you know, that regularization effect improved accuracy as opposed to just kept it the same. All right, so that's fine, but other times the bias is more subtle. And so I want to move on to this vision language model and just share one thing that we've been involved with a colleague, Professor Eileen Kaliskin. So if this is my cartoon of AI, there's inputs, there's some functions, outputs. You know, version 1 was write this by hand with Python. Version 2, as we're doing, is starting to automatically learn these things from input out of examples. That allows us to do cool things like the input is now an image and the output is a caption, fine. And more recently, we can go the other way. You give a text prompt and it spits out, you say, an armchair in the shape of an avocado, and you can get a nice photorealistic image of an armchair in the shape of an avocado. And it's really quite impressive. Okay. And so because it's so impressive, you get these kinds of claims. When we transferred our Reddit trained models to summarize news articles, they just worked. And glibv2 from Microsoft effortlessly transferred to any object detection and grounding task without further fine tuning. So this is the kind of world we're in right now. So I'll give you an example of what I'm worried about, or what Eileen was worried about, and then she kind of let us kind of play in her playground. So an armchair in the shape of an avocado produces this. And if I put in a text prompt of a 14-year-old girl, what do I get? It's not great. So if you say a 14-year-old girl, 13-year-old girl, 14, 15, 16, 17, the percentage that come back pornographic or sexualized, according to a measure that we didn't invent, there's standards out there for how to detect something, whether it's pornographic or sexualized. Nobody involved in the research looked at any of these images. It was all sort of automated for ethical reasons. As you get older here, the percentage goes up to like 60, 70%. If you go up even higher to like 18, 19, 20, it doesn't even return human pictures anymore. It's just body parts. None of that happens if you put in a 14-year-old boy. And so this idea that for any object detection grounding task, we can just transfer, freely and it's all just going to work, it's just irresponsible, right? These things trained on Reddit, you get exactly what you paid for when you train these things on the open internet, right? It's just not going to work. And so this comes back to this idea of curation is the number one cognitive task. We have to figure out how to get after these data sets, not just sort of train them on ad hoc convenience models and then sort of show different evaluations on kind of simple tasks like shrimp writing unicycles. All right. And so Eileen's really the driver of all this, not only with this paper, but she's got like 14 papers this year in everything. And she's got kind of lightning in a bottle because you can look at these psychology theories that have already been evaluated. All these things are, by the way, are true of humans. Like all these exact biases have been shown in the psychology that are to be true of humans. And she's just showing that the AI models have the exact same biases. And so there's, I won't go through it, but you should look at her work. She's just been knocking these out over and over and over again, and it's really pretty impressive. Things like American is associated with whiteness. You can any of these biases you might find in the real world, the AI models have them as well. All right. So where we're working together on this too is what do you do about it? This was kind of observational, right? It was just sort of proving in an extremely quantitatively rigorous way, thanks to Eileen and Robert's work. It's really very solid, but it's still observational. So what do we do about it? Well, can we unlearn this bias during some kind of a fine tuning like exercise, even if we don't actually care about fine tuning? And how am I doing on time? Terrible problem. Not too bad. Okay, we'll see. There's a couple of papers that inspired this. One was this women also snowboard overcoming bias and captioning models. And their observation was things like this, right? If you caption this image and it says a man with a tennis court racket on a tennis court, it got it right. That is a man, perhaps, but it looked at the tennis racket and then just sort of guessed that it was a man because most of the images on the internet have men playing tennis instead of women. And so with some adjustments, they introduced a couple of lost terms to sort of increase confidence when there was gender information and decrease confidence when there wasn't gender information. You can encourage the model to pay attention to the actual right person. In other cases, it gets the wrong answer. It just sort of guessed a man sitting at a desk with a laptop because, if you got a laptop, probably it's a man. And so they made this adjustment. So this is great, but it's specific to gender. And in particular, you have to have those gender labels during training. And so our thought is we don't always have that. There could be, only the domain experts really know what kind of biases they want to account for. And we can't necessarily just magically assume that we have ground truth labels to correct for that. So this is not real. These are not real boxes. This is just hypothetical, but you could imagine perhaps good explanations are, well, it, labeled this a nurse because it was something to do with the clipboard or a notebook or the scrubs. And maybe the stethoscope was used for doctor and the pen or something was used for doctor. But you could also get bad explanations, right? Where it looked at hairstyle or skin color or face or something else. And so we want to kind of worry about these kind of situations. So the other inspiration here was this paper, TCAV from Kim et al. In 2018, and they were focused on explanations, but they had this kind of nice idea. So this is, if I label something as a zebra, to what extent is that label being assigned due to stripedness, right? Is zebra is horse-like and stripe-like. And so the input to this thing is to come up with a bunch of images that represent stripedness. Train a little classifier to point in the direction of stripes, and then see how like the cosine similarity of the class logic with this direction. And so that was a way of explanation. So Yiwei's idea here was, can we turn that into a loss term and actually train for that to try to force the explanations to be a certain thing? And so, for example, here is, if the domain expert says, hairstyle should not be used to determine profession, this is the gradient of the decoder, which is just straight from TCAV. But we take the dot product with some kind of a vector that points towards hairstyle. And the inputs here is a bunch of random images and then a bunch of curated images representing hairstyle. And we sort of fantasize that maybe you could just do this as like Google image search, right? Just go to Google image search and type in hairstyle and take whatever you get, right? Those are somehow And we don't care in some sense, as long as you know, it's your job to kind of curate that, maybe filter out the bad ones or whatever. But once you get a concept set, a set of images that look like hairstyle, perhaps you can throw it into this and teach the model to stay away from that, right? When it's rolling downhill, don't roll towards hairstyle. All right. And we don't have results on the real problem we're interested in, which is, you know, vision with people and so forth. But I want to show you a simple experiment that I think that UA came up with that I think is quite clever. So this is colored MNIST data set, right? So it's just MNIST, but it has, you know, red, green, and blue numbers. And so we're only going to look at 3 numbers right now instead of all 10 digits. And so the idea here is that perhaps the number is analogous to profession, while the color is analogous to something, some kind of bias you want to not be distracted by. Does that make sense? All right. So the trick about this data set is that the training data has one color mapping and the test and validation have a completely different one, right? And so, and then the key thing again is we don't have labels for the protected attribute. We're just trying to give examples of the protected attribute as opposed to ground truth labels. And so, you know, what do you think happens when you train on this and test on this? I'll actually ask.
It's kind of random, right? Sometimes it'll learn the correct thing and sometimes the wrong thing, depending on the initial conditions, depending on how much it's assigned.
Well, I won't claim to be able to interpret, or haven't tried to really interpret what the model learns, but it does remarkably bad, right? It sees this red 1 and it's very, very confident that it's a 0, right? It sees this blue 0 and it's very, very confident it's a 2. And so it ends up being completely distracted by the color. So for some reason it gets these 1s probably right, probably because there's fewer pixels involved or something. It's a straight line. And so this is just the confusion matrix, and it's terrible. And then when you add this loss term, it gets a lot better. Remarkably, it's not perfect. Like, we didn't completely remove the color bias, and we're not totally sure why. We did one more experiment to try to make it even easier for us to do this, where we, you know, instead of having those kind of, these are slightly like grayscaled, right? They're kind of toned. Completely saturate the color so there's only one color going on, and then make the concept set be exactly that color, that the same RGB value. And we still didn't quite get it perfect, so we're not quite sure why that is. Yeah, we didn't really ground out the theory here at all, and I'm not sure we're going to as a sort of empirical regime. But anyway, but I thought there's a very, very nice experiment of what we're going to do. I was hoping to share some results on on the Celeb A data set. He's got some things running, but he wasn't confident about the results, so he didn't want me to show him. Okay, so anyway, but that's the kind of the idea that we really like here is let people be in the business of curating sets of images or sets of text or whatever to influence the model in a way other than just retraining from scratch. All right. The overall pitch here is maybe programming is reducing to curation. And the only point I want to make real quick is just that if you buy this analogy, perhaps there's a whole tool chain we can imagine, right? We can imagine IDEs for curation. We can imagine debuggers for curation. We can imagine unit testing frameworks and get sort of a software engineering ecosystem, but it's more accessible to domain experts who don't necessarily have programming background, but they can still influence these models and essentially write their own functions. And that's where we're headed with this, we hope. This is not really a new idea or something I came up with. I meant to make this animated and I failed to. But the hidden paper here in 2016 was Alex Ratner and Chris Ray with data programming. This is kind of an influence on this too. And what they showed was, can you take low quality labelers? You write a heuristic, you write a little Python function that says, well, every time I see a stethoscope, it means it's a doctor. It's not very good. It's not a perfect labeler, but it's a labeler. It works a little bit. And they asked the question: if you combine a bunch of these weak labelers, do you if you ensemble them in some sense, do you get a high quality labeler? And the answer is yes. And so this is quite nice. Companies really like this because this could put their army of programmers to work writing heuristics. Anyway, so this is a nice idea that had a whole line of papers after that kind of influences. And these two papers in the middle are just some of the this doesn't do it justice. There's hundreds of papers on these topics, but on the kind of problem with the empirical regime we're in with machine learning, right? So this is leaderboards and benchmarks and some of the issues with that and what we need to look at. And this is kind of influencing our thinking as well. And then this paper, I don't know if people are familiar with this one, but I like this one a lot. So these folks pointed out that this is trivial or impossible dichotomous data difficulty masks model differences on ImageNet and beyond. And what they showed was that 40% of the tasks of the data items in ImageNet are trivial, meaning that every model gets them right. And some other percent is impossible, meaning that the models completely disagree and they always disagree. And in the middle is where the action is, right? Where you can really sort of show this one's improving. And so when you start to roll up aggregate accuracy on these things, you're not getting the same number you think you are. You're measuring a lot of like sort of trivial examples and difficult examples. And I think it's a very nice point to make about the quality of the evaluation matters. And so it's yet again kind of a example in my head of like where curation really matters. Like what if you threw out all the impossible ones and threw out all the trivial ones? You might have very different rankings of models and methods and so on. Okay. So I just mainly wanted to share that. Oh, and then also, like, Andrew Ng's data-centric AI kind of whole method is obviously not very different than this either. So there's lots of people sort of thinking in this line. And then one more shout out, I guess, is Scott Lundberg at Microsoft has this notion of ADA test, where he's got a human in the loop, where the model is suggesting tests and the human kind of curates them a little bit. And anyway, it becomes a little bit a better evaluation of these language models rather than just stock tests. So this is kind of a unit testing framework for models. All right. Let me wrap up here real quick. I've sort of made all the points I want to make, but let me just share a couple other fun things that we're doing here. A few years ago, we had this partnership with some sociologists who did this eviction study, and they wanted to ask questions about who's getting evicted at how often and so on, especially in Seattle, but now it's kind of spread nationwide. And it's remarkable that nobody knows the answers to this, right? It's public data. It's a court case when you get evicted, but it's, public. There's public and there's public, right? There's public, like you can download from the web, and then there's where you have to like walk down to the courthouse and like sit down at a terminal and ask permission, and then you can like browse through them all. And so through a lot of pestering and paying some money and various kinds of tricks, we ended up getting all these PDFs in one place. And then once you have the PDFs in one place, you're not done yet, because now you have this thing, right? This is not readily accessible to sort of do anything with. But here's where, a little bit of machine learning helps. And so run Tesseract on this thing and pull out a bunch of messy data, and then train a little model to recognize addresses. And now all of a sudden you can drop things down on a map. You can, once you have a location on a map, you can look at the census breakdown by race, and now you have, and that's a fairly standard method in sociology, so that was something we didn't have to defend that. Anyway, so now you can get a sense of like who's getting evicted broken down by race. And there's a whole bunch of interesting results here, but here's maybe one that captures it. So obviously this is King County, Pierce County, and Whatcom County from around Seattle, and this is the percentage of adults that are involved in an eviction event or something. I think it's involved in an eviction event. So this is, one thing is remarkably high, right? That's 50% of like all adults involved in eviction is rough. But the other obvious feature here is this massive bar that's black. When you account for socioeconomic conditions, this bar is still there. There's no other explanation than abject racism from landlords. And there's a video that I was tempted to show, but then I chickened out, but with Tim sitting next to somebody representing the landlord associations at a hearing, and the guy is just spouting this like racist rhetoric. He's saying how the tenants are drug-addled and crazy and so forth, and trying to justify why these numbers are that bad. So it's just an absolute mess. But the remarkable thing is like a little bit of AI upstream in the information extraction helped enable the sociological research that should have been known long before. And so we like to play this game. We like to look for these opportunities. So this got picked up a few years ago and was quite satisfying to be able to. They actually changed some policy based on this. There's a few policy changes based on this work that was nice. Based on that work, Amy Hagopian reached out to us fairly recently in public health, and we're working on another task here. Bing Bing is my student, and Kelly Curtis is Amy's student. And the idea here is that hospitals pass off debt to collections agencies. So you get a patient comes in, they charge them an enormous bill, the patient can't pay, they owe $500, let's say. They sell that debt to the collection agency for $200 and then just forget about it. Right? And the collection agency goes and tries to harass them, and tries to get it out as best they can. This is not illegal, but there is a requirement that they're supposed to offer financial services to the patient when their income is low enough. And the hospitals are completely ignoring this. They don't care. They want to get it off their books as quickly as possible. And so the idea was, can we go look at the court cases for these collection agencies, find these people that deserve an intervention, and then call them up and talk to them. And this is what they're working on. But they needed help with the scalability of this information extraction problem. And so what Bing Bing is just getting started with is use layout LM types of tricks, which I wasn't super familiar with until we started doing this. It doesn't work right out of the box. We have to do some fine tuning, and that's what we're still working on. But it does sort of work. What layout element does, if people aren't familiar, is you don't just look at the text. You look at, like, it cuts up the whole thing into boxes and sort of learns all these things, and that allows you to do things like form understanding, like this is. One trick here. This is a typed number, but many of these are handwritten. So one little trick here that I'm not really sure is a big research problem, but it's a bit of an engineering challenge. Is we need to combine a handwriting recognition thing with a layout LM and sort of put that together. And somehow we haven't quite done that yet. But you can ask the question. You can say, hey, what is the gross earnings? And there's a chance that it'll find it'll through the OCR, it'll notice the words gross earnings. This is amount of suit. Sorry, I guess I should have a different picture here. We also care about amount of suit, but that's easier. What is the gross earnings? It'll look for the word gross earnings, look nearby for some form, and then pull out that number, and there's a chance it might get it right. Anyway, so then we'll pass it off to them, and they'll do that. All right, last point I want to make here, just real quick, is the scientific literature, which is maybe what's relevant for people in the room. We spent some time with this notion of visiometrics, where we wanted to look, we had a cute term for it, like bibliometrics, but for visualizations, where we want to try to understand how does the use of visualization scientific literature relate to impact and all kinds of other things. And that also led us into a little line of work where we were kind of learning, if you have access to an ontology, how do you best take advantage of that? The only point here is visualizations are important. Actually, real quick, does anybody know what this is? Science buffs?
Oh.
Earthquake stuff?
No? Good guess.
My heart rate while waiting for paper reviews.
Rattle off a beautiful
Okay.
whip, right? It's funny. It shows how similar everybody's time series plots are. I guess, right? This looks seismic. It looks like heart rate. It looks like any kind of fortune. So this is from the LIGO experiment. So this is this enormous L-shaped, super sensitive thing buried underground, and it's L-shaped because you want to get it from any direction. And as a gravity wave, which were predicted by Einstein but never shown experimentally, comes through, it'll literally stretch the thing briefly. It'll like make it physically longer in an imperceptible way, but with lasers and stuff, you can measure that. And so after putting it online for like a month, they detected these gravity waves, which was some super, like two black holes colliding billions of years ago or whatever. Anyway, so some people make t-shirts out of this because they really like the science. Anyway, but the point is visualizations are important. Like this is a memorable visualization. And there's other ones too. So we had a whole pipeline that we did. This is some number of years ago. We had to cut up the images and kind of reassemble them to try to get some figures. So there's a little like sub problems that we had to solve. And then train a model. And this is another time where we thought like, all these models that are designed for natural images won't work on these visualizations, and they kind of did. So we were a little disappointed that we didn't need to come up with a whole new architecture. So ResNet fine-tuned on scientific figures work pretty well. But once you have all the labels, once you label according to these classes, you can ask some questions. You can say, there was a previous result that said that higher impact papers have fewer equations. And people were lamenting this because it was like, well, biologists don't like math, and what do we do about that? Do we change the math and so on? And it seems to be true, right? So higher impact papers tend to have lower equations. Do high impact papers have more diagrams, like explanatory diagrams? And they seem to, right? So this is interesting. Maybe it's advice for when we write our papers. Do top journals tend to involve more or less visual information? And it's more. And so the idea here is, picture is worth 1,000 words or something, right? You want to sort of invest in the figures. Like I'm always jealous of my colleague. I do some work in visualization every once in a while, and they always have these like beautiful papers because they're so. Anyway, so we have like query prompts and so forth in databases, and it's boring. Okay, but one limitation of this stuff was equation, photo, diagram, table, and visualization is obviously inadequate as an ontology for what kind of visualization you see in practice. And so we want things like scatter plot and bar chart and dendrogram and all this kind of crazy stuff. But once we get a big rich ontology, where are you going to get the training data from? You're not, as you get a more nuanced ontology, you can't just mechanical turk this out and expect people to recognize what a dendrogram is, right? You barely can do it with this stuff. And so this gets back to that high expertise settings, right? We want this big ontology, but where are we going to get the training data from? And so this motivates us to think about this distant or organic supervision. And the observation is that every once in a while, somebody actually mentions the type of plot in the caption. I don't recommend you do this in papers. It's a bad form, but some people do it. And so that little bit of signal where you say a scatter plot of this is perhaps enough to pick up as a source of supervision. And so Max and Huifeng worked on this. And so the input here, the old work was this is actually not scientific figures anymore. Sorry, this is expression data. We did the same game, but the inputs are an ontology. That's a lot of human curation, a lot of expert knowledge went into this ontology, and then a bunch of data, and then also includes some free text as well. I mean, this is almost like quaint nowadays because of all the vision language stuff going on, but at the time it was people hadn't really done this. And then train these two networks, one on the text, one on the expression, and have them kind of learn off of each other as you go forward. And so this worked pretty well. I won't go into the details here, but the point is you could just say, you could build your ontology. Like if you wanted to include gel or electrophoresis figures in your ontology, just add it in, retrain the thing overnight, and now you get a nice set of labeled images without having to do any other work. And so it really seemed kind of cool. And so this allows us to scale with the human curation, right? If you give us a richer ontology, the model will pick up on that automatically. The more recent work that we just did was, once you have a rich ontology, why not apply some graph learning to that, learn an embedding of the ontology, also learn an embedding of whatever you're trying to classify, and then map that function. And we were kind of surprised by this, but this instantly became sort of the state of the art among this area of hierarchical multi-label classification. So hierarchical means the ontology, multi-label means there's lots of labels you can attach, it's not just one. And we were sort of better than everybody else except for like one data set, just by doing a relatively simple trick. It's been a little hard to convince the reviewers of this because it was, anyway, there wasn't all that much behind it, but it was better than everybody else at this game. So Sean's been doing a bunch of great work. We also wrote a little data sets paper for NerdRips around sort of like that dichotomous data thing, pointing out that the reason why we won so easily is that these data sets are actually pretty terrible. They're not as interesting as people think they are, and so we try to sort of articulate that. All right, so there's the last slide. So claim is data curation is becoming the operative cognitive task in these high expertise settings, and so we somehow need to enable that. And we can enable that with new putting a little bit of AI upstream to help with curation, but also methods to benefit from the curation activities that are already happening. And I try to give some examples of that. And then we see applications across all these different areas. And that perhaps next, what we're interested in is take this software engineering metaphor with it and try to see if we could really build a whole programming software engineering world where instead of writing code, you're curating data sets and using them for things. But we haven't figured out what that exactly is going to mean yet. So that's it. I ran a little long here, but there's a bunch of students. Sean's on the market soon. I'll mention that. There's a bunch of early students, and then you got some alumni. There's a bunch of sponsors here as well. So thanks so much for your attention, and hopefully it was worthwhile to you.
Time for a few questions.
I can start with one.
Yeah.
So I noticed, I was kind of curious for work that led to either like being picked up for like policy changes in government or like maybe changes in how companies do things.
Yeah.
How did that happen? Like, is that like you tried to incorporate them early on in the research so they kind of already bought into your findings, or did you wait for like Twitter trending and then people reached out to you because of it, or kind of how?
Yeah, so first of all, it should be clear, I don't deserve any credit at all for this. This was, the sociologists were in charge and we were just trying to help them out with some of the technical problems. So they were well connected and they made a bunch of noise about this when this report came out. So, you saw that splashy website that said the eviction study. They do a pretty good job with that kind of thing that I don't. I wish I had that gene, but I sort of don't with our projects. And so once it was there, he's being invited to meetings, and he's people are interested in this stuff. I mean, the policymakers wanted to know these answers, right? They suspected that there was a lot of racism in evictions, but they never had the data before, and so there was already kind of a hunger for that. And then they could point to these quantitative results that came out of the University of Washington, as opposed to some bias. We have an air of being unbiased about that. So I'd have to have Tim tell you exactly what the sequence of events was, but he was pretty well connected. He was being invited to meetings, and they were interested in making these policy changes, and the evidence helped enable that, I think, is what happened. So it was kind of poised, if that makes sense. Cool.
Bill, I was kind of wondering, when you're suggesting kind of adding this curation into the process of model development, where, like, I guess how do you imagine, like, what role do you imagine that curation taking? For example, is it someone thinks there's a sort of bias in the way the models currently are applied to this problem have, and then you want to curate some way of reducing that bias, or is it more like once the model is put into practice, like, you know, can you just tell me a
Well,
bit more about how you
I think so. I can't say, you know, I think once the model's put into practice is what we're doing now, and it's bad, right? We deploy these things, then we have to kill projects all over the place that we find out. I mean, I give a whole talk on the sort of responsibility and fairness stuff or whatever, but Amazon has been a wonderful source of ridiculous failures. So it's just insane. So you know, they'll put something out there, and then like 10 months later, some computational journalists at Bloomberg will write an article about how incredibly biased it is, and then they'll go back and they'll try to fix it. And you know, Google's done this, and everybody's done this. So anyway, so I think part of my, you know, my interpretation of that setting is that it's like releasing code without ever having run any tests, you know, or we're not running enough tests. I guess I should say we're not running any. And so I guess that's the mindset. So I would say definitely before release, you want to kind of get into this activity. And then your other question was sort of where does the idea come from? And I think it is sort of akin to software engineering, right? You think of, you know, you're not, unless you're in sort of formal methods or something, you're not really drawing strong guarantees about what your software does. You're just kind of putting together some tests that represent your interests, your requirements, and kind of crossing your fingers. And I think that might be okay in the setting as well. But right now we're not even trying that. We come up with like a single accuracy number and then release the thing. Meanwhile, there's all these other kinds of, I mean, even it's not even just bias and fairness and so forth. That you know, that's an important topic and I'm interested in it, but it's not the only one. It's also just how are the errors distributed across the data? You know what I mean? Like where are you making mistakes and where are you getting them right and so forth? And it seems like my sense is that people don't put very much emphasis on that. So I'm not sure if I'm answering your question, but I guess I'm hoping to empower the domain experts where if they come up with an idea, you know, in the shower in the morning and say, oh, I just realized that I never checked to see whether the training data had this scenario in it. They have some tools at their disposal to go check that, and then maybe also synthesize those examples or draw together more examples to try to make those adjustments. But I'm, you know, literally waving my hands talking about this. We don't quite know yet, but I mean, honestly, I'm looking for feedback too. I'm hoping people will be like, that's insane for this reason or something. So, but we're just kicking this around. I don't know if I feel like I evaded your question. Maybe with
I mean, I agree. I think there could be more analysis of how these models are working, but we don't have a principled way of putting that together right now.
Right.
It's very ad hoc. People have an idea of what maybe is broken, and then you kind of investigate it, and then continue to investigate that going forward. But
so you were hoping I had a more principled way of doing that, but
sure, or just like some ideas, yeah.
Yeah,
Like
yeah.
for unit tests, maybe you want to test every function and in under a few settings. But in these cases, there's not really a clear idea of what those units might be. Yeah.
Right. Yeah. It's not clear yet. I guess
Yeah.
Is it at the analogy stage more than the
Sure.
actual answers?
I think of using some ML products as curation too. Have you ever used Codex, the thing that
Sure.
suggests code?
Mhm.
Sometimes I feel lazy and I'll just say, I know I can write this, but instead I'll just press Control Enter and then look at the 4 suggestions and just pick one.
I have not. So yes, if I use it, I'm familiar with it.
Oh, okay,
It's
yeah.
pretty cool that you're actually building your daily workflo.
Oh, all the time. It's
Wow.
sometimes saves me time, but when I have,
Sometimes violates license agreements too.
who doesn't? If I misjudge my own tiredness and think that it can do something that it can't, then I will generate twice as much work. But if I have an accurate estimate of my own ability to produce labor, it'll cut my work in 2.
Interesting.
So then I have now an additional metacognition task of deciding whether to use it or not.
Mm-hmm.
But I think it's still worth it all after all that. So I'm imagining that sort of pattern is also curation, can also multiply as more products become ML products.
I mean, I would like to think that, you know, the Codex team, but they probably are doing some version of this, but you know, shotgun training on all of GitHub is
Yes.
one thing.
Yeah.
But maybe there's a more targeted way to do it.
Yes.
You licensing and redundancy and so forth.
Right.
That kind of activity I think is more ad hoc or not being done at all is my sense, as opposed to what kind of tooling can we imagine to support that kind of thing.
Yeah. Hopefully now they have revenue, they can be a little smarter.
I mean, the other thing, I'm not sure it's controversial or not. I kind of go back and forth, but I kind of want to evict the whole notion of a data set, like this idea of the data set. What data set did you train on? It's like, I don't really care, right? Like, it's not, it's like saying a programmer, what style did you use when you wrote the program? As long as it meets tests, it's fine. And the implication of this, if you buy that, is, again, it's okay if you synthesize some data over here, or you went and found some extra images from Google search, or you put in another code base and combined it with GitHub or something like that. Do whatever you want, as long as you are building your scientific argument that the function you train does what you say it's going to do. Anyway, so maybe I'm not sure if this is a different way of thinking about it or not. Maybe everybody in the room already thinks about it this way, but I don't like the idea of a data set. I mean, basically, I used to get this slide that was like, real data considered harmful. And the point is like, I don't want the real data, right? The real data is from the biased, shitty world we live in, right? I want the sort of
Aspirational data.
data, especially when you start talking about fairness and so forth. Like, I know what I'm going to get if I commit to only real data that came from the actual measured world. I know exactly what I'm going to get, right? It's going to have all the structural racism, all the structural sexism, and everything else, and other kinds of biases. So I want the fake world a little bit. And so what kind of tools can we support to allow you to get to that fake world is still kind of an open question. We don't really know yet.
I like the idea of a utopia that's brought about by AI overlords only fed aspirational data.
Right? I mean,
It seems the most likely utopia, frankly, from all the ones I've heard recently.
for all the utopias,
All the other ones require a lot of violence. This one just requires perfect control from AI overlords.